Check it out now, y'all.
NanoHub U, online instruction.
Well, today we start, in this lecture, we start a new topic in the course, and this topic is going to culminate in a description of electron states in solids. And so what we need to do is we first need to build up an understanding of what a solid is, and we have to be able to describe different aspects of solids that turn out to be important in the discussion that's related to electron energy states. So to begin, let's try to sharpen our understanding of different phases that a matter can exhibit on Earth. And just want to make the case, there are three different phases, right? There's the gaseous phase where you've got a collection of atoms that are bouncing around inside of a container. Typically, as you lower the temperature, these gas atoms condense, and they condense into a liquid phase. The gas atoms in the liquid phase are much more confined than they were in the solid phase. There's an interaction between the individual gas atoms. That's the only reason that they condense, right? If there were no interaction between the gas atoms in the gaseous phase, they would not condense into the liquid phase. So the fact that there's a liquid means that there's got to be some interaction between these atoms. And then the liquid, of course, can be cooled further, and this collection of liquid atoms can then be condensed into a solid phase of matter. And for the sake of argument, I just like to make the distinction between the polycrystalline and amorphous state of solids, and then also a crystalline state of solids. The polycrystalline and amorphous state of solids is what happens if you rapidly cool a liquid. And what happens is the liquid solidifies in such a way that the individual atoms are not ordered in a regular fashion. If, on the other hand, you take a liquid and you slowly cool it, the chances are that the atoms that comprise the liquid will have enough time to find their minimum energy location. And when they find their minimum energy location, very often you'll find that the atoms condense into a crystalline phase of matter, which is highly ordered, right? It's very highly ordered, and it's characteristic of most metals and semiconductors and many ceramics. So the interesting thing is that there are significant differences between the properties, the macroscale properties of the gas phase, the liquid phase, and the crystalline phase of matter. And of course, investigating these differences and measuring them has been a topic of interest in solid state physics or condensed matter physics for well over 100 years or so. We can't possibly discuss all the measurements that have been performed and all the different properties that characterize the different phases of matter. So what we're going to do is we're going to focus on this crystalline phase of solids, and we're going to try to describe to you the nature of electron states in this solid and how electricity is conducted by those states in this crystalline solid. So I think the point to make is that these crystalline solids are found everywhere. You can find an individual rock anywhere on the planet Earth. And more often than not, if you look very carefully at the microstructure of this rock, you'll find that it's comprised of small, tiny grains that have all crystallized in this crystalline state of matter. Some of these crystalline states turn out to be very valuable, very useful, right? Some of them have been used to form gemstones, jewelry, various forms of which I've shown here, right? You have the more mundane form of crystalline solids, which is just grains of salt made out of sodium chloride. So these crystalline solids are found everywhere, and they're characterized, the general the general feature of these crystalline solids is that they're characterized by atoms that occupy ordered arrays. So just to make that point, you'll see pictures like this all over the web, where these balls represent the different atoms that condense into these crystalline phases of matter. The different colors represent different atoms, different chemical elements, basically. And the point to take away from this diagram is that these crystalline atoms, these crystalline solids, contain ordered arrays of atoms. And these ordered arrays of atoms produce very interesting properties for the electron states that exist inside these solids. So the first question is, how do you understand and how do you measure the position of the atoms in these solids, in these crystalline solids? What are the techniques that are available for you to investigate where these atoms are? Possibly the most useful and the most widely used technique is that due to X-ray diffraction. This technique was first invented back in the 1912 time frame. It was actually pushed by two separate groups, one in Germany, that was by Lowy, he was 1912, and then there were two scientists in England, the Bragg father and son team. They also pursued this X-ray diffraction in and about 1913. So both Lowy and Bragg are founders of this particular field. And what they showed was that if you took a beam of X-rays and if you collimated that beam so that you basically defined a very narrow stream of X-rays, if you push those X-rays or allowed those X-rays to fall onto a crystalline solid, it's understood that the crystalline solid is made up of ordered arrays of atoms. Right? If you then looked at the X-rays scattered from that crystalline solid, which you found on, let's say, a nearby screen or on a photographic plate, you found a collection of spots. The collection of spots also often ordered themselves in highly symmetric patterns, and the symmetric patterns that were observed was directly related to the symmetry of atoms in the crystalline solid. So these X-ray diffraction micrographs, I like to call them a fingerprint of the crystal structure, because if you can understand these X-ray diffraction patterns, you can actually infer the position of the atoms in these solids. So we've already discussed this briefly. If you go back to lecture 2.01, the basic physics of this is that you've got an X-ray beam that's incident on a crystalline solid. You consider the X-ray beam to be partially reflected from both the top plane and the second lowest plane in the crystalline solid. If these partially reflected beams of X-rays constructively interfere on a distant screen or photographic film, if the interference is constructive, you'll get a bright spot. If the combination of these two beams is destructive, the film will remain black. And so by measuring where the bright spots are and by knowing the angles and geometry of the X-ray beam with respect to the crystalline solid, you can start to get information about the inner atomic distance of the individual atoms that make up the solid. So the problem, of course, with this very simple discussion is that if you have, let's say, an ordered array of atoms, right, you can imagine drawing many different crystalline planes with respect to that array of atoms. And I just sketch out a few of these crystalline planes here. And so the challenge is to work out simple formalism to describe how this X-ray beam interacts with these different planes and predict where these regions of constructive interference are going to occur. So that's the That's the problem that besets this discussion. So again, this is a diagram that you may remember from the second week of lectures. What I represent in this diagram is just two planes of atoms. The two planes of atoms are indicated by these horizontal solid lines. I've got an X-ray beam that comes in. This X-ray beam comes in at an angle theta with respect to a line which is drawn perpendicular to these crystallographic planes. Part of that X-ray beam is reflected from the top surface, that's indicated by the blue line. Part of the X-ray beam is transmitted and is reflected from the second plane of atoms, that's indicated by the red line. You imagine that the red line and the blue line emerge parallel to each other and eventually strike a distant screen. And the question is then going to become, what's the difference in path length between the blue line, which is indicated by the blue line A, R, and D? What's the path difference between that line and the line which is indicated by the red, A, B, and C, right? So after this point, right, the two lines are parallel, so there's no path length difference. If there's any path length difference that occurs, that's going to have to happen in this region of the diagram. And then it's just a simple question of geometry to sort out what that path difference is. So the path difference is going to be given by this distance AB plus BC, that's the red path, minus the difference AR and RD, that's the blue path. So that's the path length difference. From the construction that I've got drawn here, you can see that the distance AR is equal to the distance BC, so that drops out of the equation. And you're then left with a calculation of the difference between this distance AB and this distance RD, as I've indicated here. The relevant diagram for the path length AB is indicated by this solid triangle. And what you find is that AB, this distance, is just equal to D over sine theta. The distance RD, okay, can be calculated from this other shaded diagram here, right? Need to do a little simple geometry to realize this angle is 2 theta. And the path length difference, or the path length RD, is then given by D cosine 2 theta divided by sine theta. And you want to take the difference between those two path length differences, and if that path length difference is equal to an integer times the wavelength of light, then you're going to get a constructive interference. And so you can work through this arithmetic, and at the end of the day, you get this very famous condition, which is known as the Bragg condition. It says that if the wavelength of the incident X-rays lambda times an integer n is equal to 2d sine theta, where d is the separation between these crystalline planes, then you're going to get constructive interference, and that constructive interference is going to end up as a bright spot on your photographic film, right? So these bright spots here can always be indexed back to the crystalline structure of the solid by knowing the angles and distances between the various planes in the crystal. So the problem again is that the problem is that there are many different crystalline planes in the solid, and so that if you imagine an X-ray beam coming in, right? So the incident X-ray beam is indicated by the red line, right? That red line is going to interact with different planes that I've indicated in the solid, and the relevant angles are shown in each case, right? The relevant angles are the angles with respect to the perpendicular axis drawn through these planes. And so, for instance, in this case here, the relevant angle is theta 3, and it's not clear that for this orientation of the X-ray beam and for this definition of the angle theta 3, it's not clear whether Bragg's condition is actually satisfied. So it becomes important to be able to understand how you can manipulate this experimental situation in order to prove out Bragg's condition. And so I'd like to work through that in detail for a particular example, just to give you a sense of how this problem works out. What we imagine is we imagine an X-ray beam that's monochromatic. So somehow we've eliminated all wavelengths from the X-ray beam except one particular wavelength, which in this diagram I indicate by lambda. We imagine that X-ray beam interacts with a sequence of parallel planes. The separation between these parallel planes is given the generic symbol D, and there's going to be some angle theta that's related to the orientation of these planes of atoms, right, with respect to the incident X-ray beam. And the question is this condition n lambda equal 2d sine theta satisfied for this particular value of theta and for this particular wavelength lambda that we've chosen to do the experiment? And the answer is, in general, no, it's not. What you have to do is you actually have to rotate these planes physically. So you actually have to physically rotate the crystal until this condition is satisfied. And when this condition is satisfied, then you'll see a bright reflected beam, diffracted beam from the crystallographic planes. So to try to illustrate that in a little bit more detail, just let's work through an example real quick. Let's say we have a sample with atoms, and let's say the sample of atoms has got a distance d0 between each atom, as I've indicated. So there's this square lattice of atoms present. We can define a crystallographic plane as indicated by these gold lines, right? And the separation between these gold lines can be calculated based on this known distance d0 between the individual atoms. We further imagine that a monochromatic X-ray beam, right, comes in and it strikes one of the flats of this crystalline sample. So we imagine we have a crystalline sample that's oriented or that has a shape like this. We take this crystal, we mount it, and on a movable mount, and we align things so that the incident X-ray beam comes in perpendicular to one of the faces of this crystal. So from the geometry that I've drawn, right, the incident angle, the value of theta that appears in Bragg's law is this angle 45 degrees, right? That's by construction. And I guess the point is that for this angle of 45 degrees and for this incident wavelength of 0.25 nanometers, right, we're gonna pick a unit cell D0 of 0.53 nanometers just to pick a number, right? For those conditions, Bragg's law is not satisfied. So how do you make Bragg's law satisfied? Well, what you've got to do is you've got to tilt the crystal, right? And so you've got to start to rotate the crystal, and in the process you're rotating these crystallographic planes with respect to the incident X-ray beam, which is fixed. And eventually what you're going to find is you're going to find an angle. In this case, I worked through the arithmetic here. The Bragg angle is going to have to be about 19.5 degrees in order for you to get a diffracted beam in the detector, which you can measure. And so that just simply means that you're going to have to rotate the crystal backwards by an angle of about 25.5 degrees until Bragg's law is satisfied. So you can do simple checks like this, right? So if, for instance, you measure the amount of X-rays in a detector as a function of this rotation angle, what you would expect to see is you would expect to see a sharp rise in the diffracted X-ray beam when this rotating angle equals 25.5 degrees. And then that would confirm, right? That would confirm that the separation distance between the atoms is what you actually thought it to be, which was, I think, 0.53 nanometers. So this is just an example of the type of experiment that you have to set up in order to use Bragg's law to unravel the crystal structure of crystalline solids. Just a very simple example to give you the idea. So what we have to do next is we have to start to define conventions about crystalline solids and try to explain to you some of those conventions so we can start to use them to describe the position of these atoms in crystalline solids. And what I'd like to make the point is that each crystalline solid is made up of a unit cell, and the unit cell is basically the smallest increment of atoms that you can make that when translated through 3 dimensions reproduces the crystalline solid of interest. So for instance, if you just imagine a unit cell as being one of these simple toy blocks that kids often play with, right? In principle, this toy block has the shape of the cube, and so inside this unit cell, which may contain different numbers of atoms, right? Inside this unit cell, you've got the building block for a macroscopic crystal. So you can imagine if you assemble these unit cells in 3 dimensions, right? I've got a simple toy model here. If you imagine assembling these unit cells in 3 dimensions, you can fill all space and you can produce a crystalline structure that has the same symmetry as all the atoms that are contained in the unit cell, right? So that's point B, that the unit cell exhibits the maximum symmetry of the crystal, but that symmetry is all contained in a small cell, which may contain different atoms. This unit cell has to have the same symmetry, and by that I mean it has to, if you translate it, you rotate it, or you reflect it about some axis, it has to have the same symmetry as the crystalline solid that you're trying to build up. The unit cell itself is defined in terms of 3 axes and 3 angles. And so I try to indicate that here in this picture. So I indicate this is a generic unit cell. It has a length along the x direction designated by A. It's got a length in the y direction that's designated by B. It's got a length in the z direction designated by this parameter C. The relative angles are also represented by the Greek letters alpha, beta, and gamma. And those angles do not necessarily have to be 90 degrees. It just depends on the crystalline solid of interest. So knowing the dimensions of the unit cell, A, B, and C, and knowing these angles, alpha, beta, and gamma, we'll see in the next lecture that allows you to specify an awful lot about the crystalline structure that results when you stack these unit cells to form a macroscopic crystal, right? It's important that you also realize that inside of a given unit cell, there's going to be atoms that are positioned. And these atoms are positioned to mimic the entire crystalline solid that you actually observe when you grow these materials. And when you specify the position of atoms, you very often use something referred to as atomic coordinates. And these atomic coordinates are always given in terms of the unit cell dimensions. So even though there can be a Cartesian coordinate system, x, y, and z, and the axes x, y, and z are all at right angles with respect to one another, the unit cell could have axes A, B, and C, right, which do not necessarily align along the coordinate axes x, y, and z. And so the position of the individual atoms in this unit cell are always given in terms of fractions of this dimension A, fractions in this dimension B, and fractions of this dimension C. So for instance, an atom that's positioned in the center of the face of the bottom of this unit cell, right? the position of that atom would be designated as 1/2, 1/2, and 0, because it's located 1/2 of A, 1/2 of B, and 0 in the Z direction, or in the C direction, 0 in the C direction. So the atom positions are given by this sequence of fractions, and these fractions represent the unit cell dimensions A, B, and C, not the coordinate axes X, Y, and Z. So that's an important thing that you have to understand if you're trying to characterize crystalline solids. So this is just a real quick introduction. In the next lecture, we're going to investigate this in a little bit more detail. And in particular, we're going to start to characterize the symmetry and character of these unit cells. So that'll be the topic of the next lecture. So thank you for your attention, and we'll see you for the next set of lectures.